So yesterday we discussed about the orthonormal basis set and the Gram-Schmidt orthogonalization process. So now let us discuss the Cauchy-Schwarz inequality. Okay, so first let us derive this Cauchy-Schwarz inequality. Okay, so while deriving this, you will understand more about the use of Ket-Bra notation. So suppose I have a vector ket phi plus a psi. So this is a vector and where a is a complex number. Okay. So if I take any vector, for example any vector chi, what will be this quantity? This quantity will be always greater than or equal to 0, right? So this one will be greater than, or because when will it become 0? If it is a null vector. Okay. So this will be always a positive or 0 number, right? So if that is the case, so if you call this as chi, this vector as chi, what is bra chi ket chi is equal to? So can you quickly tell me, whoever has understood to take the dual of a vector and take the inner product? So I have basically done an inner product of ket chi with itself. So what will be the first term? Okay, so what is bra chi from here? What is bra chi? The ket vector. Bra phi plus a star bra psi. Okay. So bra chi is equal to bra phi plus a star bra psi. Okay. So then I can write down this as, okay, I will do it explicitly. Okay. So some new students are also there in the class today. So let me explicitly do this. So bra phi plus a star bra psi. So that is bra chi. So what I am doing is bra chi ket chi. Okay, the inner product. So with ket phi plus a psi. Okay. So this is the inner product of ket chi with itself. So this will give you the norm square of this vector. So this, if I expand it, how many terms will be there in this?
4 terms.
There were 4 terms. So what is the first term? First term is bra phi ket phi. Yeah, so bra phi ket phi is basically the norm of that vector square. Yes or no?
Yes, sir.
Yes.
Yes.
So what is the next term? A bra phi ket psi. Next one is a star bra psi ket psi ket phi. Then the last term a star is mod psi square. So basically that is nothing but, okay, I can just write down this way, okay, so to have some understanding. Okay, So this quantity should be greater than or equal to 0. Okay. So if it is not a null vector, this quantity will be greater than 0, right? If ket phi plus si is not a null vector, then obviously, so this is greater than 0. So for that, your a should not be equal to, a psi should not be equal to minus phi. Okay. So a psi should not be equal to phi, minus phi. So if phi is equal to minus a psi, you get a null vector. So then that condition is not satisfied, so it is greater than 0. Okay. So now substitute a. Suppose I want to cancel this brass psi ket psi from the term. So I can actually substitute a is equal to minus psi phi. Can I substitute something like this? Can I substitute this one in this equation? Is there any problem?
Sir.
Yeah, because a is general a complex number. Okay, so I can choose any complex number here, except ket phi should not be equal to minus a psi. So if I substitute this one, that is a is equal to minus brass psi ket phi. So in this, is it a complex number? Yes, because brass psi ket phi is the inner product of two general vectors, that is in general complex number. This is, the denominator is basically a real number. So what is a star? If a is this, what is a star? Minus bra phi ket psi divided by same thing. Okay. So now let us substitute a in this expression, and what are you going to get? So first one is, okay, the norm square. So next term a, that is minus psi phi psi divided by psi, and the next term is minus phi psi, then divided by psi, then psi phi, and the last term is, so one brass psi ket psi will cancel with the one brass psi ket psi, because this is a star. So a star, there are two brass psi ket psi, inner product of psi with itself. So one of them will cancel out. So denominator you get one brass psi ket psi, and the numerator, what are you going to get?
Brass psi ket phi and ket phi.
Brass psi ket phi and bra phi ket psi. That's it, right? Right? Which is greater than or equal to greater than 0. Okay. So can you simplify this? Is this term and this term same?
Yes,
Or is these three terms same? Yes. So what you can get, and also multiply all the terms with the norm square of psi. So multiply brass psi ket psi with all the terms. Okay. So what are you going to get? So what is bra psi ket psi? It is a norm square of psi vector, right? So you get so 2 minus, so 1 plus, so this is bra psi ket phi, bra phi ket psi. What is bra psi ket phi, bra phi ket psi?
Modulus of bra phi ket psi square.
Modulus of bra psi ket phi square. So minus modulus of bra psi ket phi square, which is greater than 0. So I can write down this as square is greater than okay. So I can take the square root because this I can write as mod phi mod psi is greater than bra psi mod phi. Okay. So this is basically the Cauchy-Schwarz inequality. Okay. So what is basically this? The norm square of one vector into the norm square of the second vector is always greater than the inner product of those two vectors modulus square. Okay. This is a very useful formula or identity. Okay. So this formula actually using this formula we can derive the uncertainty relation. So what is the uncertainty relation? Because I just telling you now, okay, delta x delta p. Anybody knows about the uncertainty relation? H cut or h cross by 4 pi. Okay, you decide about this number. Okay, the important thing is the uncertainty in x multiplied with uncertainty in p is always greater than one number h cross by 4 pi. Okay. So that means, so this all of you know because all of you are basically the physics students. Okay, you know that it is basically saying that you cannot measure the position and momentum of a particle simultaneously, okay, with a infinite means accuracy, okay, because there is always an error in the measurement. This is not because of you are not able to measure. It is actually built in the quantum mechanics, okay, because it's not your inability to measure. It is actually the system cannot give you more than that accuracy. Because if I give you delta x is, so what is delta x? Delta x is a variance in x. Okay. So delta x is a variance in x. So the variance, if you make it 0, that means the variance in x, suppose you are measuring the x, the position of a particle with infinite precision, delta p will goes to, according to this relation, will goes to infinity. So this is basically the idea. So maybe we may derive later in the course, or you will derive this in the your quantum mechanics course later on for the UG students. Okay, the PhD students may be already knowing these things. So to derive this, you basically use this Cauchy-Schwarz inequality. Okay, so that is importance of this Cauchy-Schwarz inequality. So to derive this, you have to understand more about the operators and all. So I will not get into that now, but understand that this is a very important inequality. So you can also derive the triangular inequality from this, because these are all the vectors. All of you know the triangular inequality. So you can actually go ahead and try to solve the triangular inequality. Okay. So now let us look at the change of basis. Suppose there are two orthonormal basis set. One is set ket phi i's. Other one is set chi i's. So there are two, because how many number of basis set you can have in a given linear vector space? How many is possible? Infinite number. Okay. So now I am just giving you two bases. Okay. So they are actually orthonormal basis. So what do you mean by orthonormal basis? Bra phi I phi j is equal to delta ij. Also bra chi I chi j is equal to delta ij. Okay. They form a complete set. Yeah. So now you take any general vector psi. Now let me expand this because they are basis vectors. I can expand ket psi in terms of ket phi I. So how do I expand? So this is the basic idea regarding the basis vectors, because you want to expand any vector in that space in terms of those basis vectors, so that your calculation may be simpler. Okay, because usually in quantum mechanics these basis sets are the eigenstates of, okay, so I will tell you what you mean by an eigenstate when I talk about the linear operators in vector space. Okay, but you understand because you already know the eigenvalue and eigenvector problem. So eigenvector problem is basically eigenstates. Okay, because there you may be done with 3 by 3 matrices and found the eigen. Do you know eigenvector and find out eigenvalue and eigenvectors of a matrix? Any idea?
No, sir.
No.
No, sir.
Okay. Okay. So we may discuss. Let us see at the end of this course. If you are not learning from any other course in the institute, okay, you tell me. Okay, that the eigenvalue and because as a linear operator, I will teach you what are they, but according to the matrix, you have to learn. Okay, because that we can also do little bit, but I know that the mathematics department will teach you more about that. So I don't want to repeat those things. Okay, so right now you for some idea regarding that, if you take a quantum mechanical system and take the energy operator, which is basically the Hamiltonian, its eigenstates form a basis. Okay, eigenstates are vectors. Okay, so basically I have an operator. I will discuss about this little later. So they have an operator. I can put a cap here. It's an operator because you already seen an operator which is basically the projection operator. Okay, so there are so many other operators. So operator acting on any state, say alpha, if it is equal to alpha ket alpha, so this is the eigenvalue and this is, so ket alpha is an eigenstate. So any operator acting on a state giving you the same state with a number alpha, so this is basically the eigenvalue equation. Okay, and alpha is the eigenvalue and this is the ket alpha is the eigenstate. So H is the Hamiltonian or the energy operator, if you want to say. So the eigenstates depends on which dimension you are talking about. So in that dimension, the H, that suppose it is an n-dimensional vector space, then there will be n vectors, n eigenvalues in general if there is no degeneracy. So we will discuss about the degeneracy later on, because some of you may be already knowing about that, but let us not get into that. So in general there are n eigenvectors. So those n eigenvectors form a basis. Okay, because of that any state in that Hilbert space. So any state in that Hilbert space is basically any physical system in that Hilbert space. You can write it in terms of those eigenstates. So this is the basic idea. That is the reason we are doing all these things. Okay, it's not just purely a physics math course. So we have to little bit understand why we are doing it and what is their role in physics. So that is why I explained that. So now this ket phi I is a basis. So any state I can, in that space, I can write it in terms of ket phi I. Okay, so that is what we are going to do now. Yeah, so let us, the two-dimensional plane, you have a x cap and y cap, and I have general vector, some vector v. So I call this s cap as E1 and y cap as E2. Then I can write down this ket v as some coefficient C1 ket E1 plus C2 ket E2. Okay. Now let me consider some other vector, the basis vector, which is you call it as say F1, ket F1 and ket F2. Okay. So that V, then again the same V I can write it in terms of ket F1 and F2. So in that case I may get some coefficient D1 E1 plus D2 E2. So this C1 and C2 are the components of this vector V along E1 and E2 respectively, and so this is, yeah, so yes, you are correct. This is F1 and F2, and D1 and D2 are the components of the same vector along ket F1 and ket F2. Now this C1 and C2 will be different from D1 and D2, right? Yes or no?
Yes, sir.
Now my question was very simple. Okay, suppose C1 is equal to D1 and C2 is equal to D2. Question is whether ket E1 is equal to ket F1 and ket E2 is equal to ket F2. So that was the problem I had given to you. Okay. In general, I can find any number of basis vectors, and the given vector I can write it in terms of those basis vectors. Okay. So the coefficients will be different. Definitely the coefficient will be different for a different the basis vectors. So that is what I am talking about here. So your question is clear now?
Yes, sir. Yes, sir.
Okay. So now I have two vectors, basically two basis vectors, ket phi I and ket chi I, ket chi j. They are different basis vectors in n dimension. So I am taking any general vector psi, I am expanding it in ket phi I. So di ket phi I. Obviously the same vector I can represent in the ket chi j also. Okay. So this is, so I can use, okay, so earlier I think I used C here. Okay, does not matter, anything I can use. So let me use di here. Okay. So Ci n di. So this is I is equal to 1 to n, and this also j equal to, so this is j, so j is equal to 1 to n. Fine. Is this clear now? So same vector I expanded in the basis phi I, and the same vector I expanded the basis chi j. So this quantity is equal to this quantity as a full sum, but individual Ci and dj's may be different. Okay. So my earlier question was, if each individual Ci's and dj's are same, does that mean that ket phi and ket j are same? Okay. So that is the question. So any vector you can write it in terms of the basis vectors. Now how do I find out these coefficients? Okay, I want to find out, I want to write down what is Ci equal to? From this expression, what is Ci equal to? I want to find out that. Okay. Where ket phi are the orthonormal basis vectors. If ket phi is our orthonormal basis vectors, so if I multiply this equation from the left side, bra phi j, okay, so bra phi j ket psi, what do I get in the right hand side? So right hand side, summation I is equal to 1 to n Ci bra phi j phi I, right? So I just multiplied this vector. Actually, I took a inner product of ket psi with phi j, where phi j is the one of the vectors in that basis set. Okay. So what is this quantity equal to? What? Ci delta ij or delta I, because delta ij is a symmetric tensor or symmetric means symmetric tensor basically. Okay.
So should it be Cj?
Yes, definitely. Okay. So this is equal to Cj. Okay. All of you have understood this? If you do not understand how this is Cj, I can explain. Otherwise, I will move ahead. Okay. So these coefficients are Ci. So what will be Ci equal to then? Bra phi I psi. So what is then Di? Can you quickly tell me what is Di equal to?
I multiplied by
Chi I multiplied with the
net
psi.
I.
Okay. So this way you can actually find out the coefficients. Okay. So to find out the components of the vector, actually you can actually take this. You take your vector, multiply with the which component you want, that component along which basis vector you want, take inner product that with, and you get this. See, all these things you know in your Euclidean space, the Cartesian coordinate system. Okay. So I am writing it in a different notation, that's it. So now, whatever we said, I have two basis vectors, phi I and chi j. Now, I have two vectors, one is ket psi, other one is the, so these are different vectors, okay. So I can put this way, okay. So I have two vectors, ket psi and ket phi, and this is a basis set and this is another basis set. Now I want to find out the inner product of this vector with this vector, okay, and write down that inner product in terms of either the component along this vectors, the basis set, or component along this vector basis set. So how do you do that? So this is, so what is the inner product of ket psi with the bra phi? So I can do this phi with psi. So what is this equal to? So you know that ket psi I can expand in terms of ket phi I as, say, Ci ket phi I. Okay. I can expand in ket chi j as say di ket chi, let us put j chi j. So the other vector, the phi vector, so phi vector also I can expand. So this is psi and this is phi. Okay. So the phi vector I can expand with some other series. So say E I in phi I. I can write it as f j chi j. So all these things are clear. So now let me find out phi with psi, where phi and psi are expanded in phi I and chi j. Okay, so means so ket psi I can expand it in this form, and bra phi I can expand it in this form. So what will I get? So what is bra phi from here? Summation I. Can you tell me what is bra phi from here?
Summation of
EI star
Draw phi.
bra phi I. What is ket psi? This one. In the same basis. Okay, we have to find out the inner product in the same basis only you should do. Okay, so if you are finding an inner product, you have to find out the inner product is like this. You have to do it in the same basis. Okay, so that is basically equal to Ci. Is it correct? What I have written is correct?
It has four double indices.
So let us use a different notation here, Cj phi j. Okay, so there are two summations. Okay, summation on I and j. So what is this quantity equal to? What is this quantity equal to? Quickly you tell me.
E star I by Cj
Three stars
del ij.
del ij.
Ei star Cj delta ij. What is that equal to?
Ei star Cj.
Ei star Cj delta ij. So this is equal to Ei star
Cj.
Ci. Okay, so you got this. So now you already know this, how to get it. So what will be the inner product of these two vectors in the chi j basis? Can you give me quickly the answer?
fj star dj.
So the phi psi in the chi j basis will be equal to the phi is so this is psi, so phi is in the star, so fi star dj.
So fj star dj.
Fj star dj. Okay, so you found inner product in one of the bases, you got this answer. You found the inner product in the another basis, you got this answer. Are they same? The question is, are they same?
Yes, sir.
So what we have to do is find out whether the inner product in the basis ket phi I and the inner product in base in ket chi j for these two vectors ket psi and phi are same. So that is what we want to find out. Okay. So you can see that in the ket phi I basis, what you are getting is Ei star Ci, and the ket chi j basis you are getting Fj star Dj. So what you have to do is you have to show that Ei star Ci is equal to Fj star Dj. So the question is, how do you write down Ei and Ci in terms of Fj and Dj? So if you can do that, so if you can write down Ei and Ci in terms of Fj and Dj, then we may be able to show that this is equal to that one. Okay. So so what we will do is, from this equation, let us write down Ci in terms of dj. So what you are having here from the equation 1 is summation Ci ket phi I, okay, which is equal to summation dj ket chi j. So if you multiply this equation with the bra phi j from the left side, suppose you take the inner product of this with the ket phi j. So what you can see is this equation will become C j Cj, right? So basically how that has happened, so we can clearly see that. Let me just do that for your convenience. So I am just multiplying bra phi j, okay, then so this is I, okay, this is I. So here summation dj, okay, so I think we should not use the same index j because we already used j here. So let us multiply with the bra phi l, okay, that is better. Okay, I multiply with the bra phi l to the left hand side. So here also you do that, phi l chi j. So here what you get is Ci delta IL, Ci delta IL, so that will become Cl. So Cl is equal to dj phi l chi j, okay, summation. So we got now Cl or Ci in terms of dj. So similarly, you can write down Ei. So what will be that one is equal to? So you can write down by the understanding of how you got this equation. So you can write down Ei is nothing but Fj bra phi I chi j. Okay. So from this equation you can get Ei is equal to Fj. So there is a summation over j. So now in this equation you can substitute. So Es star will be the conjugate of this, and Ci you can actually Ci will be equal to, you just replace L with I in this equation. So if you substitute that, you can see this equation will become in terms of Fj star, because Ei star is there, Fj star and dj. But there are other terms in this, but that you can easily show that using the completeness relation, okay, the other terms will cancel out. So that you can completeness relation, and using the orthogonality relation of this ket phi i's and ket chi j, you can easily now show that Ei star Ci is equal to Fj star dj. So I am giving that as an exercise. Okay.